Welcome back. We're going to continue on in Chapter 2. And in Chapter 2, we've been discussing how objects move. And we've been talking about that in terms of distance, displacement, and speed and velocity. And then we talked about acceleration. Again, in keeping with our let's do the simplest case first and the more complex, we're finally getting into a little bit more complex areas where we're going to start talking about something called uniformly accelerated motion. This is when an object is going to have a constant acceleration that is not zero. Now, it is the simplest type of acceleration. It is one that we're going to have continue to move in a straight line. We're not going to turn yet. Turning is more complicated. Now, in this case, because the object has a changing speed, we're going to have a whole new set of equations to deal with. So what we're saying here is that we're going to talk about, so all of these are going to have a constant acceleration. Constant, and it's not going to equal zero, and it's all going to be moving in a straight line. We're going to worry about turning later on. But when we have this constant acceleration in this either the same or opposite direction of our velocity, this allows us to come up with a whole new set of equations called the kinematic equations. And these are three equations, plus an add one we should already know, that allow us to determine distance, displacement, speed, velocity, and acceleration in time when we combine all those together. These are called the kinematic equations, and they're extremely important to know. You will use them from here on out. I'm not going to say every single day, but pretty much in every single chapter, you will use these equations for our remainder of our time together. Now, these equations, you can find them in your reference table, but just for quick reference, remember so far we've gotten that our average velocity is displacement over time. We've said that our acceleration is the change in the velocity over time. I should do delta t. There you go. Okay. So those are the two we've had so far. Now there is one other one that I'm going to tack on. And this is one that you should know from previous math classes and stuff like that. But it's just our average. That we take the average, let's say our final plus our initial divided by 2. So anytime you want to find the average of two numbers, you just add them up and divide by 2. So this is one that's not listed on your reference tables. If you want it there, I encourage you. You can write it right on there so you can have it. Or we use these to come up with our other kinematic equations. Now, the other kinematic equations are just variation or combination of these three. The first is just a rewrite of our acceleration. Now, I do have to speak really quickly because I'm pretty sure I mentioned this in class, and if not, I will mention it again. But because we're dealing with multiple velocities, we just can't write V. We like to use subscripts to know which velocity we're talking about. So in this case, I wrote VF. That's my final velocity. VI is my initial velocity, acceleration, and time. So this is the first kinematic equation. And it's just a rewrite of our acceleration. The next one, and I'll put this in orange, it allows us to find the displacement of an object when we know the initial velocity, the acceleration, and the time that that object is undergoing that acceleration. And then our third one, which I'll put here in, I'll do a nice light blue, allows us to find the final velocity. We know the initial velocity, the acceleration, and then the distance that acceleration occurs. These equations are crucial. You will have to know these. Very, very important. We're going to spend a lot of time practicing with them, okay, identifying what they are, and we'll be talking about something called the guess method. This is going to help us solve these problems shortly. Now, the best example of uniformly accelerated motion is actually objects that fall down. Galileo was the one that showed, and there's a myth that he would drop things off of the Leaning Tower of Pisa. He would drop a stone and a heavier rock or something like that. And what he saw is that regardless of the mass, those things would fall at the exact same rate. And so he came up with this idea that these things would accelerate, change their velocity at the exact same amount. In the absence of air friction, this has been proven, okay? For our purposes, it's pretty close, okay? So What he stated was that he showed the body will speed up as it falls, and that acceleration is a constant 9.8. And in our case, just now write this in, the Regents likes us to use that acceleration is 9.81 meters per second squared. You'll notice that I used a new symbol. This symbol is a lowercase g. It is still an acceleration, but it's now not just any acceleration. This is the acceleration due to gravity, and this is a constant that we can find on our reference tables. So as you drop an object, if it falls for 1 second, its speed will go from 0 to 9.81 meters per second. After the second second, it's going to speed up another 9.81, so 19.62, and so on and so forth. And so it speeds up as it falls. Okay? This acceleration is a direct result of gravity, and gravity is something that we will talk about in later chapters. Okay? There's a gravitational pull of the Earth on all objects that are on it. And its symbol, as we saw on top, is a lowercase g, and its value is 9.81 meters per second squared. Now, this is an acceleration, and it means it is a vector quantity, which means it does have a direction. We're going to write it as 9.8 meters per second squared down, okay? And that down is going to be very important later on, especially when we get into chapter 3 and we start moving in different directions. Okay? Now, when an object is thrown upward, it still has gravity acting on it. If I throw this object up, it slows down until it gets to the top. And so initially, if my initial velocity is up, I know that my acceleration due to gravity, I'll put that in green, is down. And so what that's going to cause it to do is it's going to cause it to slow down, slow down, slow down, slow down, and kill it until it gets to the top. Now, after it gets to the top, it's going to start coming back down. So now our velocity is down. Our acceleration due to gravity is still down. And so that's going to cause it to speed up as it falls. Now, the one thing that causes people an issue is what happens when the object gets to the top? And I'll just put this in. So if this is their object going up and then coming back down, what happens when it gets to this part right here? And a lot of people like say, well, okay, yeah, it's got to stop. So my velocity at this point in time, my v, is 0 meters per second. And what a lot of people think is, oh, then my acceleration has to be 0 meters per second as well. But that's not true. It is still acted out by gravity. So the acceleration due to gravity, even up there, is still 9.81 meters per second squared down. If it wasn't, if that acceleration was 0, that velocity would never change, and this object would stay at the top the entire time. Now, when we come in tomorrow, we're going to do a lot of more practice with this. We'll change our kinematic equations. We'll get practice with those, and then we'll use those in terms of an object falling as well as some other constant acceleration. So be prepared to practice tomorrow, and everybody have a great night. Bye-bye.